I'm here to talk to you a little bit about KenKen, also known as Calcadoku, and a question from the blog of Brian Hayes. So in KenKen, or Calcadoku, the goal is to solve a puzzle. What you're trying to do, like in Sudoku, is find a Latin square solution. So each entry only appears once in each row and once in each column. The grids are divided into cages, and you have clues. And when you solve the puzzle, the entries in each cage have to give you the clue number when a particular operation is used. And the operations are given in the puzzle. Many of you may have heard of Brian Hayes. He also wrote for Scientific American and American Scientist. And he maintains a blog called Bit Player. And he was writing about KenKen when, just as a side note, he talked about a 4x4 puzzle over the complex numbers. So it wasn't the focus of his entry, but I liked what he said after that. He said, I'm not at all sure the solution is unique or that it can be found by a purely deductive process. At best, this is a joke KenKen. And this was the puzzle he gave. It's all multiplication, and there's some complex numbers. We have I, -1, -I in there. So I'd like to talk a little bit about how to solve a puzzle like this. And probably the best thing you can do in the beginning is to remove the only interesting thing about the puzzle, and that's the fact that the puzzle's over a cyclic group of order 4, so you just map it to another cyclic group of order 4 that you're used to working over, and we can pretend this is the integers mod 4, and you turn it into that puzzle there. And there's another trick you can use, because in the two cages, the entries are next to each other, and we have a Latin square condition, so we can't have the same entry twice. Whenever a clue is even, it restricts the possibilities for the two entries in some order. So using these two things, working over Z4 and using that fact, you can get to a solution fairly quickly and then map that back over to the complex numbers. Though that's not what I wanted to talk about, because this brings up a whole bunch of questions about these types of puzzles. I mean, is there always going to be a solution? Is the solution going to be unique? If not, how many solutions can a board have? And notice there was that nice little diagonal thing going on. Does that have anything to do with the uniqueness of the puzzle? So we can answer this first clue really quick. Does any set of clues produce a solution? Because there's 4,096 possible clue sets, but there's only 576 possible Latin squares. So not all of these puzzles are going to be solvable. If a solution exists, is it always going to be unique? Well, maybe perhaps the most roundabout way of solving this is this proposition, saying that if the center clues are both equal to some same even number, there's always exactly 8 solutions. Now, there's one argument for why there can't be more, but those are the transformations that give you all 8 once you've found one. You could ask if the diagonal pattern has anything to do with the uniqueness. It doesn't. If the entries on the off diagonal have a certain parity condition, then you're not going to get a unique solution. And how special was that pattern of cages anyway? Well, there was one very special thing about it that's very basic, and that's the fact that it had some cages that had 3 cells in it. Now, you need to have odd cells, because if the number of entries in each cage is even, then the solution would not be unique. And this is very easy to prove, because you could just add 2. Remember, we're working mod 4, so if all the cages have an even number of cells, you're just going to get a new solution by adding 2 to all the entries. Okay, well, he had this nice x and y symmetry when he made up the cages. So you could ask, and we know we need an odd number of cells in some of the cages, so we can ask how many possible boards are there that he could have chosen. And there's really only 3. And you could see that the first 2 there, really they look the same. You could picture yourself putting one on top of the other and making a puzzle into a different puzzle using the first 2. The third one looks a little different, but when you remember that you have this Latin square condition, each row has to have 0, 1, 2, and 3. So if you have 0, 1, 2, 3, 0, 1, 2, 3, the top half has to add to 0. So it actually doesn't matter whether or not you have those 2 cells in there, because the top half has to add to 0, the bottom half has to add to 0. So the clues in those 2 cages are going to be completely determined. So there really is only that one board. And there is a way of determining when there is a unique solution. It turns out that there is a unique solution whenever 3 of the 4 clues are equal and the other clue happens to be a different parity than the other 3. You can map that over to the complex numbers and get the rule for the type of puzzle that he suggested. You can also ask how he chose the puzzle. And I was trying to get the number 11 out of here. I ran some Python code. You could say, well, if he just picks a Latin square at random, the odds of the solution being unique would be 1 in 18. And if he picks clue sets until he finds one with a solution, then I get a 33 in there, but I couldn't squeeze an 11 out of that. But what I can say is, if you start with this Latin square and you use this to generate a puzzle, there will be exactly 11 other solutions to that puzzle. So there you go. Thank you very much.